This is A2U10L1 sequences and series. The biggest part of these first couple lessons is going to be vocabulary and formulas, so you'll be needing to take notes on this. You'll probably need to pause in order to get it all down. A sequence is a list of numbers that has a pattern, like 2, 4, 6, 8. That's a set of numbers and they have a pattern. They grow by 2 each time. We have finite sequences, which are limited, and infinite, which are unlimited. Now, an example of each one, 1, 2, 3, that's a finite sequence because it ends at 3. This sequence, 1, 2, 3, with your set of ellipses, that's those 3 dots, this is unlimited. It keeps on going. Now let's talk about term notation. This is the shorthand or the language of sequences and series. Capital A with a subscript of 1. The subscripts give you a location. So A to the 1 is always your first term. All the other terms in the series are notated as A to the N. So this is your subsequent terms or your following terms. Now here's an example of an infinite set. 1, 5, 9, 13, 17. Let's locate these terms. This is number 1, 2, 3, 4, 5. They just go in order. Notice there is no 0. When you are identifying your term places, there's no 0 because if you didn't have a spot at all, you wouldn't have a set. So A sub 1 is 1. Alright, what is A4? 13. It's in the 4th position. Alright, A9. I don't have A9, so we're going to have to expand this set. Let's look for the pattern. What is the pattern from 1 to 5? 4 was added. From 5 to 9, 4. You see that pattern repeats, so that's our rule. Alright, what is 17 plus 4? 21. And 21 plus 4 is 25. And 25 plus 4 is 29. You see how it just keeps extending. And 33. And 33 plus 4 is 37. So let's see what term we need. Number 9. Here's 6, 7, 8, 9 is 33. This is 10. So I need 11, 41, and 45. So our 12th term is 45. And this is your term notation, okay? A sequence can operate as a function. Now remember, a function is just where you put one number in and you get another number out. So when we look at a sequence, we can have a domain and a range. Now in your sequence, your domain is the set of term numbers. So that's their position, like 1, 2, 3, 4. This domain is over the set of natural numbers. Now remember, your natural numbers start with 1. There is no 0 in your set of natural numbers. So you're never going to have a 0 in the domain of a sequence. Your range is going to be your set of term values. So your domain is term numbers, and your range is term values. So the domain of our sample set here would be 1, 2, 3, 4. Oh, no. Your range would be your term values. 1, 5, 9, 13, 17. We're fixing to look at 2 different kinds of sequences, recursive and explicit. Now your recursive means that each term in your sequence is based on the previous term. So like you're adding 2 each time, or you're multiplying by 2, but you're doing something to the term right before it to get to the next term. Now this means on a recursive sequence, if you need to find the 15th term, you're going to have to find terms 1 through 14. You can't just skip over to it. Now an explicit sequence is based on the term number. That's its position. You're going to have formulas for these terms. So on recursive, that formula is going to include the term right before it. For explicit, the formula is going to be built on its position. So for explicit, you can jump to the 56th term and you'll be able to find just that term. So let's look at some examples of each one first, starting with recursive. So let's look at some recursive sequences. Now, in sequences, a rule means the formula for the term so that you can skip around and find whichever term you want. One famous recursive sequence is the Fibonacci sequence, and it starts off with 0, 1, 1, 2, 3, 5. When you look for a pattern here, the pattern is that you add this plus this to get this one. And then you add this term and this term to get this one. And it just continues on. You're going to add the two previous terms to get the next term. That's what makes it recursive, because you can't find the 100th term without knowing terms 98 and 99. Now, as far as notation goes, if I'm looking for some unspecified term, A to the N is going to be that term number, all right? How do we get from Fibonacci? What would be our rule? Well, you're going to take A to the N minus 1 plus A to the N minus 2. So let's just look at this. These subscripts tell you the position. So what this rule is actually saying is that to find the nth term, whatever number that is, you are going to add the term that comes before it. If this is A to the N, A to the N minus 1 means back up one space. A to the N minus 2 means back up one space. So that's how these subscripts are going to help you find your term. The N minus 1 always means the term just before the one you are looking for. So look at it as a whole thing. This is a position that tells you what to do with the numbers in that position. So let's look at an example. We're given that A1 is equal to 14 and AN is equal to A to the N minus 1 plus 9, with N is greater than or equal to 2. And we want to find the first 5 terms. So let's just put some blanks down here. And we're going to fill these in. Now our first term is given to us, so that's 14. This is term number 1. And I want to find 2, 3, 4, and 5. Now these numbers down here are N's. So our formula is right here. This is our rule. And what about this down here where it says N is greater than or equal to 2? Well, if you'll remember, I told you that the domain of these is greater than is 1 or more. You can't have a 0. Well, we've already got 1. So we're going to be looking for all the N's that are 2 or more. We want to start with 2. So let's look at our rule. A to the N minus 1. What does that mean? It means the term before the term you're looking for. We're fixing to look for term number 2. So if I take this rule, I want to find A2. Well, if 2 is now my N, my formula says 2 minus 1 plus 9. All right, what's 2 minus 1? So A1 plus 9 is my rule. Now I can substitute. What is A1? I have a value for that. So 14 plus 9 is 23. Now if you look at it, you have an even more basic rule. What you're going to do is you're going to add 9 to the previous value. So if I add 9 to 23, I get 32. If I add 9 to this, I get 41. If I add 9 to that, I get 50. So that's how to apply your rule. Let's look at one more example. Now let's try this one. Our first term is going to be 6, so we can go ahead and put that in here. Our rule is A to the N is 2 times A to the N minus 1 minus 5. Now remember, this right here just represents the term before. Whatever term I'm looking for, this is the term before it. So now, if this was number 1, I'm looking for term number 2. If I filled in these numbers, I'm looking for the second term. That's going to equal 2 times. All right, what is A to the N minus 1? Well, Well, 2 minus 1 is 1. So what is my A1? 6. So what this is actually saying is 2 times the term before it minus 5. And 12 minus 5 is going to be our next term. So that's 7. Now let's move on to the next one. What if I want to find A3? Well, this is 2 times. Now a to the n minus 1 is 3 minus 1, which is A2 minus 5. So what is A2? Well, it's the term you just found. The one before, the one you're looking for. So that's a 7. And 14 minus 5 is 9. Now you can see what you're going to do is you're actually just going to multiply 2 times the term before and then subtract 5. So instead of writing it all out, let's just see if we can do that. 2 times 9 is 18 minus 5 is 13. 2 times 13 is 26 minus 5 is 21. And you would just continue on. 2 times and minus 5. 2 times and minus 5. That's the pattern that we have going here. Next, let's go backwards. We're going to look at how to write a rule for the recursive sequence right here and then give the next 3 terms. First of all, there's a reason it says write a rule, because it is possible that you could find more than one rule. So there's not just one right answer. If your answer works, if it progresses through the terms that you're given, then your rule is right. Alright? When it's recursive, your next sequence depends on the number in front of it. So I've got to look for a pattern between this 4 and 11, and then 11 and 32, and 32 and 95. So right off the bat, I can tell it's not going to be just a simple add a number or subtract a number, because the difference is not the same. So let's look at a ratio or multiplying. Well, 4 times 2 would be 8, which is close to 11. But 11 times 2 is 22, so the difference just gets bigger and bigger. So I'm thinking that's not it. Let me go ahead and try 3. What happens if I multiply 4 times 3? Well, I get 12, which is only 1 away from 11. If I take 11 times 3, I get 33, which is only 1 away from 32. If I multiply 32 times 3, I get 96. Once again, that's only 1 away. So that looks like my pattern right there. So let's see what we had to do. If I want to find, and I'm trying to write a rule for a to the n, what did I do to my previous term? Well, I multiplied 3 times. 3 times what? How do we notate a previous term using term notation? Remember, you use the a. Well, if this is a to the n now, if I've moved over 1, this becomes n minus 1. This is your position. So if you are looking for n, you want to refer back to n minus 1. And then we subtracted 1 every time. So this is going to be our rule. Now I already know 1, 2, 3, 4, 5 terms. So let me find term number 6. Here's how you apply the rule. A6 is equal to 3 times. Alright, a to the n minus 1. Here's n. So if I do 6 minus 1, I'm looking at A5, right? Minus 1. Now, what is A5? Let's substitute. That was 284. So when I multiply 3 times 284, I get 852. I'm going to subtract 1. So my next term is 851. All right, now let's look at how to find the 7th term. So my A7 is going to be 3 times. All right, what's n minus 1? 7 minus 1 is A6 minus 1. What was A6? We just found it. 851. So if I do 3 times 851, I get 25, 53, minus 1 is 25, 52. And now I have one more term left to find. So I'm going to need A8, which is going to be 3 times A. All right, 8 minus 1 is 7 minus 1. What is my 7th term? 2552. So now 3 times 2552 is 7656 minus 1. My 8th term is going to be 7655. So I know that is a little difficult and it does take a lot of practice. So just keep trying on it. Just look for patterns. It will get easier, and I'll be honest, finding the pattern in a recursive sequence to me is a lot harder than any of the others that we're going to look at. So hang in there. Now we're ready for explicit sequences, and I promise this is much easier. An explicit sequence or an explicit term is defined as a function of n. The previous term is not necessary. So that's your definition. So you don't have to go all the way through. You can find term 56 without knowing what term 55 is. Let's find the first 5 terms of, and here's our rule, an is equal to 7 times n minus 3. If I want to find the first 5 terms, 1, 2, 3, 4, 5. Remember, your term numbers under here, that's n. So all you have to do is substitute the term number for n, and then you get the term value. So if I want to find 1, if I put 1 in here, 1 minus 3 is negative 2. 7 times negative 2 is negative 14. Let's find term number 2. If I put 2 in here, 2 minus 3 is negative 1. And 7 times negative 1 is negative 7. All right, term number 3. 3 minus 3 is 0, so 7 times 0 is 0. If I put 4 in for n, 4 minus 3 is 1, and 7 times 1 is 7. My last term, if I put 5 in here for n, 5 minus 3 is 2, 7 times 2 is 14. See, I told you, explicit sequences are going to be much easier to deal with than recursive. And next, let's look at how to write a rule for an explicit sequence and give the next 3 terms. And here's the sequence we're looking at. We're given the first 5 terms, so we want to find terms 6, 7, and 8. Now, in an explicit sequence, you're not going to refer back to the previous number every time. There's going to be a constant number in there that you are just manipulating each time. So there's one thing that's going to be the same, or one or more things, and then there'll be something that's different, and that different thing is going to be based on the sequence number, okay? So let's look. What I like to do is make a chart with my values and my sequence terms. So my numbers, my n, is just going to be their position in the sequence. 1, 2, 3, 4, 5. The a to the nth is going to be their value. And the value of my first term is negative 7. The value of my second term is negative 9. 3 is negative 11. And on down. Now, to come up with a rule, and your rule is going to start out with an equals. I need to find something basic for each one, and usually that base is something to do with your first term. So let's just start with the term itself, negative 7. What did I have to do to negative 7? How did I manipulate it to get negative 9? Well, one thing I could have done is subtract 2 from it. Let's see how that plays here. If I start with negative 7 again, I already had negative 7 minus 2 from here. I just subtracted 2 more. And then this one, I took that one, subtracted 2 more. This one, the same thing, same number, but I subtracted 2 more. So you see here, the negative 7 is your constant all the way down. So that's going to be a part of my rule. Negative 7. Then what did I do to it? Well, I subtracted a 2 a version of 2. Let's see what the relationship of 2 was. Here for my first term, I had no 2 at all. Here for my second term, I had 1 2. Here for my third term, I had 2 2s. Here for my fourth term, I had 3 2s. And for my fifth term, I had 4 2s. So notice my factor of 2, my multiplier of 2, was 1 less than the sequence number. So let's write it as n minus 1. So this is what you're saying. If you want to find any member of this sequence, any term in this sequence, you can take -7 and you can subtract 2 times that term number minus 1. So let's apply it to the 6th term. If I want to find A6, I'm going to take -7 minus 2 times. Alright, n here refers back to this number. So 6 minus 1, which is 5. So now I have -7 minus 10, which is -17. So that's this number. Alright, now let's find term number 7. Now this is the great thing about explicit. It doesn't matter what the term before it was. I could actually find term 107 using this formula, and I wouldn't need to find all the 106 terms before that. So let's just give it a try. Let's say I want to find I want to find A7, and I shouldn't have erased my formula. So let me see if I can remember. It was -7 minus 2 to the n minus 1. Alright, so for 7, I'm going to have -7 minus 2 times 7 minus 1. -7 minus 2 times 6. -7 minus 12 is -19. And then my last one, if I need to find A8, that's going to be -7 minus 2, n minus 1, 8 minus 1 is 7. So I've got -7 minus 14, which is -21. Now let's jump into series. We've been looking at sequences. Now we're moving to series. A series is the sum of the terms in a sequence. So you have to have a sequence before you can have a series. When you have a sequence and you add all the numbers up, you get a series. That's all there is to it. If you have an infinite sequence, then your series value is going to be infinity because there's no way to add them all up. A partial sum is the sum of a specific number of terms. So if it just asks for the sum of the series, you want everything. But if it says add terms, 5 through 8, that's a partial sum. Now our notation, you're going to see S subscript n. The n is going to be how many terms you're supposed to add. Like S to the 5th would mean add the first 5 terms. Alright, so there's your vocabulary. Now let's look at summations or summation notation. And there's this big scary looking thing. This is the sigma, and it's really shorthand. This is what it means. This number down here is your first number. This is your first term. This number down here is the last term that you want to sum, and this is the formula. So what this actually tells you in long words is take the numbers from 1 to 5, fill them into this expression and get a value, and then add all those values together. That is a summation. So let's do this one. 1 to 5 for 2n. So I'm going to take 2n and I'm going to substitute 1, and I'm going to substitute 2. 2 times 3 plus 2 times 4 plus 2 times 5. Starting number, ending number with the formula for each one. So let's do the math. 2 plus 4 plus 6 plus 8 plus 10. And then we're going to add them all together. So here's 10, 28 plus 2 is 30. That's all the big scary sigma thing is. So let's look at one more summation notation example. We have the sigma. We want to take -3n and we want to fill in every number between 1 and 7, find those values, and then we're going to add them all up. So it is tedious, but it's not hard. I'm going to have -3 times 1 plus -3 times 2 plus -3 times 3 plus -3 times 4 plus -3 times 5 plus -3 times 6 plus -3 times 7. 1 to 7, all times -3. So let's get the values. -3 plus -6 plus -9 plus -12 plus -15 plus -18 plus -21. If you add all those up, you will get -84. Okay, that's all there is.